Hi, I'm going to be telling you about the Nanotechnology Engineering program here at the University of Waterloo. Our program within engineering here is a program that is next to several departments of engineering, yet also implicates a lot of faculty from science. So we are really a trans-faculty and multi-department program where students can figure out really what they find most interesting in the science and engineering world. When students ask me what is nanotechnology engineering, they typically on the very first day say, this is what family and friends are asking them. And nanotechnology engineering really started maybe over 50 years ago when Richard Feynman said, and this was even before his Nobel Prize in Physics, that there's plenty of room at the bottom. And really what he was thinking about in terms of the world of miniaturization is that if you can control the chemistry and physics of systems that are increasingly small, then the opportunity to try to make things that are targeting specific chemical outcomes and physical outcomes really is powerful. So we envision this by controlling atoms and molecules as you build something. And here we say building from the bottom up. So imagine joining atoms and molecules one at a time for a targeted material with a very specific kind of property. Then you have the power to really kind of target what you're looking for, whether it be a material, a drug, or any other in between. So this is different than imagining something that is broken down, so top down, where you take a material and you cut it into a billion little pieces. So bottom up and requires a strong, powerful background in terms of chemistry and physics. And really what happened in terms of nanotechnology engineering is that it really started to blow up and have massive implications when the scanning tunneling microscope was invented. And so what we see now is a process where we can vision and actually see, but what I mean by see is detect really, and have signal from something that is an atomic resolution. So here you can see even the graphite surface, where one atom at a time is detected using a tip. And where you have to imagine now, how thin does a tip have to be in order for it to be able to detect one atom at a time? And I'm going to mention the scanning tunneling microscope now because later you'll see this is the challenge that we gave to our first year students to build such a device. So nanomaterials really are not just surfaces, but they're really also particles. And now we're talking about any system where you have a large surface component, and that's what's going to be driving the chemistry and the physics of the process. So thin films, as well as nanoparticles, are really a much larger component of what we talk about in nanotechnology engineering. So at UW, as I mentioned, we're within a large engineering school. We have well-established programs around us who have been around for now many years, and now I'm thinking chemical engineering, electrical engineering, but we also have some newer programs, newer than us even. We have biomedical engineering, architectural engineering, so this is always a growing and developing field, and nanotechnology engineering sits within this and interacts with all of these disciplines of engineering, as well as with science. We have faculty, the teaching to our students who are also on the faculty of science, as I am in the Department of Chemistry, bringing students an opportunity to have really broad interests. So just like I had no idea I was going to find myself in nanotechnology engineering, most of our first year students, they don't know what they like. They know that they kind of like the sciences and the engineering, but really, where is it that they want to find themselves? They don't know. And I think this is part of our program is really broad and allows for students to really explore all of these ideas and maybe find something they never knew existed that they realize they're really good at and they now really like. So this is also part of our UW and Nano Engineering program. Our home is called the QNC building. This is the Mike and Ophelia Lazaridis Quantum Nano Center. So this was built now several years ago, maybe 8, where students are in these classes in this building. Many undergraduate students there in one time, although some are sometimes overseas with co-op. We have hundreds of graduate students in a variety of departments. Again, we put them in a building so they can interact and learn from each other. So chemical engineering graduate students or chemistry graduate students, electrical and mechanical, find themselves sharing space and instrumentation and expertise. Researchers are there. We have highly specialized equipment. So the scanning electron microscopes that our students are using, the clean room for the microfabrication of semiconductors is there. So really, this is a center where we're trying to hope that new things and new ideas come when people with different expertise work closely together. Our students then have impact from chemical engineering, electrical engineering, and chemistry, so that they can understand really everything that they need to as a core concept. So these are our core courses, and then be able to kind of branch out on their own. We are, as with other engineering departments, have co-ops, so our students end up all over the planet, and we'll tell you about that more in a second. And this is already an accredited program. We've had now many graduating classes. And I'll tell you a little bit about those students. So in terms of the very first term, so I see students on the very first day. And on the very first day, I say, I know where you're sitting now, and chances are you'll sit in the same seat on the very last day, and often that's exactly the case. The students now, you can see a graduating class. This is one of our typical classes in the QNC building. On their very first term, they have really what looks like a typical set of courses that an engineering or science student would take. So they have calculus and linear algebra in terms of mathematics. They have some programming. They'll either have a chemistry course, which was my course, or maybe perhaps a physics course. And what they also have is what we call the societal environmental impacts course, which is really about the legal and ethical issues associated to a licensed programming. And this kind of accreditation programming requires us to tell them this is what it means to be an engineer, and you're going to have to at some point understand the implications for that in terms of nano. So we start to talk about all of those issues on the very first day. And so it seems like it's actually quite normal in terms of a very first term, and we don't see the sort of breadth of different types of courses until we get to the higher term courses. And here, the higher term courses, now you start to see a much varied opportunity for our students. So these are all core courses. These are courses that all our students would take. But now you're starting to see some really large variation, where on some side, you will get some organic chemistry, some biology, some biochemistry. So really now we're talking about how do nanomaterials interact with biological surfaces? How do we make them? How does it implicate sort of drug delivery? Those ideas, polymers and materials, and toxicology courses, how are they an adverse effect if you're exposed to it? That's one side of the material. And then we have sort of standard courses really in statistics, advanced calculus, and numerical methods and programming. So this is always going to be used by all our students, really kind of independently of what they find really interesting. But also now on the physics side, we have something for our students to learn about electronic circuits and devices, how to have microfabrication and nanofabrication processes, and clean room use, semiconductor physics. So these are now starting to really sort of increase the breadth of our students. They have a foundation in the engineering and science, and now we're moving them across to what's really becoming what we call a horizontal discipline. And after this, now students realize there's some things they really like, and some things, not so much. But now, as technical electives, now I really see students branching out. So we have an opportunity for students now in their third and fourth year to choose the laboratories that they really want to excel in. And typically at this point, they've had several co-ops where they found really an interesting work. Sometimes I tell them, hey, on the co-op, at least you'll decide, you'll know, you like it, really not for you, or maybe it's something that's really stimulating your interest. And often they come back and they say, I want to change my technical electives. I now really want to explore this whole other side. And you can take courses in biomedical engineering, systems engineering, in sciences. So now they each individually choose what's right for them. And this is really, I think, the power of the nanotechnology engineering program, is to allow such a wide aspect to our higher and more specialized courses. For co-ops, our students are all over the planet. in academia. So this is, they're in laboratories, whether they're doing drug design over at Harvard or MIT, or they're making materials in a variety of established industries, software, consulting, and hardware. They are so diverse that sometimes some of these jobs really are very difficult to compare to each other. So it really is dependent on the student. It depends really on what they find super interesting. And so they come back, they understand how to apply this to their courses, and go from there and choose their appropriate technical electives. So to tell you a little bit about how we motivate our students to try to think and apply what they use in their courses is this first year design engineering project. And we just finished one just a few weeks ago, where we have the students build a scanning tunneling microscope. So they're building something to try to detect a surface with as high as possible resolution. And I told them on the very first time that they were going to do this, this was now a few years ago, I said, the bar is so high here that a lot of faculty really don't think there's going to be a single functioning device. And I think they took that personally. They took that and ran with it, and several of them ended up having completely very functioning devices. And you can see them here. They're building cages to suspend their detectors. They, of course, want to have vibration isolation so that there's no vibration in the room that's impacting their tip. Their tip that they had to make, which was part of how I was implicated in the program, had to be made with such tip and fine resolution so that they would be able to scan across a disc and try to see the grooves that we have imprinted there for them to detect by tunneling electrons across surfaces. That tip, a few of them had to remake their tips, and they came to me and they said, well, what happens if your tip fell on the floor? And I said, there's still time. You remake a new tip, because if you've lost your tip and that capacity to have that kind of resolution, then your device isn't going to be really functioning. They absolutely rose to the challenge, and we are super proud of what they were capable of doing. On the very first year, they made friends, they worked in groups, and they realized, apply what you know in your courses to make something that you never thought possible. And here, now I'm going to move to my fourth year design projects team. So in our fourth year courses, all the engineering departments will have a fourth year design projects, where the groups are formed on individual students, and then they will, on their own, then come up with something that they think is worthy of a new design project. And the faculty of the Nano program are super proud to have the 2020 Canadian Engineering Competition for Innovation Design Award winners, the national champions from the Nanotechnology Engineering team. This is Han, Darren, Dan, and Luke, and they formed this new material called Smart Coat. And I have to mention at this point that Nano had a very sad event with the passing of Darren, and I think the whole fourth year team really kind of brought themselves together to realize they have to support each other when things happen, and the unexpected and the tragic, and the rest of the team pulled together to really come out with a fantastic process. And here I want to show you what they sent to me that I wanted to share with you was their Smart Coat. And so here you can see really what they've made is something for as an impact detector, really. And now we're thinking, how could this be used in terms of detection of impacts both individuals and to materials? And so they've used the nanotechnology idea of, let's embed in small materials and small particles something that has a different signal depending on its state. So this is very much nanotechnology engineering, and you can see from these two colors, a polymer bead that's embedded when not broken versus one that's undergone an impact and has released a dye looks completely different, right? And so if this is going to be used as concussion prevention, or if this is going to be used for materials that need very special care, this team came up with something that was obviously recognized nationally, and we're super proud. So they know how to look at problems, they know how to group together and apply their courses. This is really another idea of what's happening at nanotechnology engineering. So in terms of general fields, I mean, this is, as I mentioned before, a really horizontal discipline. This impacts both materials that we talked about. This could be biological materials. This could encompass a variety of other drugs and or signaling materials. And I think what you have to realize is that each of these we build in terms of fundamental courses, but then the students go and discover what they really like. And if you were to explode that into the kinds of devices and materials to study, now we're talking biosensors and drug delivery processes, new semiconductors and thin films, right? The nano instrumentation, how do you build materials with that kind of fine tip resolution, right? The energy sector with the batteries of the future that perhaps aren't going to be based on lithium ions, right? Or have a variety of other type of photovoltaic possibilities. This is a now very broad field. So while nano engineering is not one field, I think the students start to realize it's embedded and part of all of this, all of them, and many fields. So to summarize a little bit about what's special at UW, I would say initially we give them the breadth. And this is a broad curriculum. I talked a little bit about how in the first and second year, they're going to be taking courses both on organic chemistry, biochemistry, both physics, and into the world of semiconductor physics and computations, and a very wide set of courses so that later they can choose on their own. Really, what is it that they find the most interesting? They can choose their labs. Do they want to have a nano instrumentation lab in the clean room and microfabrication process? Or would they rather go and do drug delivery and DNA sequencing? And so really, all of those possibilities exist. And I think that's really where our students start to realize there's a possibility and probably a road here that's just right for them. And here I've shown you our graduating classes, another one of them. They end up graduating from our program, ending up in either small startups, they could be local, right, or in Canada, they're in established industries, larger pharmaceuticals or materials industries. And many end up in graduate programs too, doing PhDs in either engineering or science, realizing that they want to come back with perhaps some PhD experience to come in, do some really good work in terms of research and development in the field of nanotechnology engineering. And then there's those who end up in professional schools, other professional schools, such as medicine or law. And so I think now the opportunities really depend. And for you, it's going to be, what is it that you want to do? And if you don't know what you want to do, that's okay. Give yourself the time. We open up a few doors, and I tell students this is really one good thing about the nanotechnology engineering program is we will provide you with a variety of doors for you to choose and expertise in areas that you don't even know. Of course, the difficult things now is that you have a variety of doors and you have to figure out what it is you like. And that comes with time. Talk to your faculty, talk to your friends. And I'd love to see you in the nanotechnology engineering department on the first day of class.
Hi, my name is Emma Beliveau, and I'm here today to talk about my student experience in the Nanotechnology Engineering program. So I'm from Nova Scotia, and I originally, like many of you guys, didn't really know what I wanted to take in university, but I knew that my favorite subject in high school was chemistry, and specifically the lab portion of that course. So I decided I wanted to pursue something in that field for my undergrad. But I wanted a more design or engineering-based approach than just taking chemistry in the science faculty. And I've ended up really enjoying the degree. So far, I figured out my areas of interest over the past few years are fabrication methods and materials for optoelectronic devices and solar cell materials and scale-up. Throughout the program, I've had the opportunity to have a variety of co-op experiences through the program, and these have included my first one, which was a 4-month co-op at the summer after first year, which was at the University of Waterloo, where I was doing research on soil treatment of oil spills using nanoparticles. For my second 4-month co-op, which was in second year, I had the opportunity to travel to Taiwan to join a university research center there, where I researched novel material solar cells. For my third co-op, which was 8 months and in third year, I decided that I wanted to try an industry position, which was in the semiconductor industry, where I worked on R&D for image sensor design for industrial and specialized cameras. Finally, for my final co-op this year, from January to August, I worked in Cambridge at MIT in the Grid Edge Solar program. And there I was researching flexible and printable solar cells. Outside of the academics of this program, this year I am the VP Academic of the Nanotechnology Engineering Student Society. So we plan events for people in the program and advocate for its students. I've also been in the Guelph Pipe Band, which is a community band in a nearby city, and where I play the bagpipes. And I've also taken part in an academic exchange, which I did last fall to the National University of Singapore, which was one of the highlights of my undergrad. Now I'll pass the presentation off to Kingsley.
Hi everybody, my name is Kingsley Wong and I'm also a fourth year nanotechnology engineering student. I'm originally from Ottawa, Ontario. So the reason why I chose nanotechnology engineering was because in high school I had very broad interests in all three science classes that I got to take, so chemistry, physics, and biology. So instead of narrowing it down to just one, I decided to choose a program that lets me work in all of them. So along the way in high school, I became fascinated with the idea that you can use these traditional sciences and redesign a whole new set of tools at the molecular scale. And as a result, I decided to continue to pursue that idea at the University of Waterloo in the Nanotechnology Engineering program. So along the way, through my academic coursework and my co-ops, I've developed particular interests in using biology as a tool to create and fabricate materials for energy and electronic devices. And the second one is using DNA, so the biomolecule DNA, for biotechnology applications. And that includes using it for sensors, using it, or developing platforms for synthesizing DNA and platforms for sequencing DNA, which is essentially just reading the molecule and extracting information from it. I've had a variety of co-op experiences. My first co-op experience after my first year was as a research assistant at the University of Waterloo, where I was working with a professor to study the interactions between nanostructures and mammalian cells. So just more specifically, that's looking at how cells will respond in different environments and different media and how they interact with different structures. My second co-op was at a startup called Arilla. And Arilla is a really cool company because they use nanotechnology to develop an invisible ink that they can use to tag luxury goods. And the idea behind that is this invisible tag serves as a means of anti-counterfeiting. So a way of authenticating between what's real and what's might be a fraudulent product. My third co-op was at another startup called Kinoda Health. And at Kinoda, I was working to develop a medical device for rapid testing of allergies and rapid diagnosis. So I was working on various components of the device itself. So I got some experience working with optics and mechanical engineering, as well as working with bioassays in the biomedical field. My last co-op, which I completed, or started actually, I started in January, was at Twist Bioscience in California. So Twist Bioscience is a company that has many projects that are rooted in using DNA as a foundation. But the project specifically that I was working on their silicon chip DNA, or silicon platform for DNA synthesis, and integrating that with molecular data storage applications. So using DNA to store videos, storing files, et cetera, and also being able to directly read them. So one thing I wanted to mention about the co-op program at Waterloo is that the co-op program, it offers you a lot of support and resources for helping you find your co-ops. So for example, my co-ops at Arilla and Kinoda Health, I found directly through job board postings through the co-op program, where they post opportunities from potential employers, which you can go to and apply for. But they also support the students who want to look for their own opportunities outside of the job board. So that's how I actually arranged my first and my fourth co-op at the University of Waterloo and towards bioscience. And I did that by looking for these opportunities on my own, and with the help of the co-op program, I was able to secure those. So outside of academics and co-op, I've had the opportunity to get involved with a couple other things as well. So the first one that I'll mention is the Waterloo iGEM Synthetic Biology Design Team. And this is it's an interfaculty design team that works on an annual synthetic biology project. And each year we get to go to Boston and we compete, and it's a lot of fun. And it's a unique opportunity to work with students from all different backgrounds. And in addition to that, I also help out as an orientation leader every year. And this is an opportunity to help first-year students transition from high school to university. And that's always a lot of fun. And lastly, when I was in high school, I was really into the music programs. And I played in concert bands, I played in the jazz bands. So when I came to Waterloo, I also continued with music through the jazz ensemble at the school. And with the jazz ensemble, not only did I get to go and rehearse and practice with a full band, but we also got to perform at concerts every once in a while. So there was a lot of awesome extracurriculars that I've been able to do over my time in addition to classes in co-op. Thank you so much for joining us today, and we hope that this was an informative session and that it helps you with your decision in the future. Thanks so much, and enjoy the rest of your days.